Tables of thermodynamics properties. Tables of thermodynamics properties. Tables of thermodynamic properties of many substances are available, and in general all these tables have the same form. In this section we will refer to the steam tables. Also in the next chapters we refer to with also another tables, for example another substance table. The steam table are selected both because they are a vehicle for presenting thermodynamics tables and because steam is used extensively in power plants and industrial processes. Once the steam tables are understood, other thermodynamics tables can be readily used. Several different versions of steam tables have been published over the years. The set included in Table B1 in Appendix B is summary based on the complicated with the behavior of water. It is very similar to steam tables by Kinnan, Keyes, Hill, and Moore published in Table B1 in Appendix B. Similar to the steam tables by Kinnan and Keyes. Hill and Moore. As shown in this picture, this is the table that was provided in the book Thermodynamic Properties of Water, Saturated Water. Table B11 by the Kinnan, Keyes, Hill, and Moore in the We will concentrate here on the three properties already discussed in the chapter 2 and the section before, namely Tp and the T, temperature, pressure, and the specific volume. Pressure, specific value, and note that the other properties listed in the set of table B1, U, H, and S will be introduced later. They are internal energy and entropy and enthalpy that will be discussed in later chapters. The steam table in Appendix B consists of 5 separate tables and indicated in the figure here. Is given in Table B, figure 3.8. The region of superheated vapor in the figure for example superheated in the table B13. This is the table B11 and the next table is B12. to B13 for the superheated, and that of the compressible liquid is B1 in the next, in the left side of the pressure, temperature, specific value diagram. Table B1 for the compressed solid region shows in the figure is in the table. Appendix B is not presented. This area. The saturated liquid and the saturated vapor region as seen in the figure before is listed according to the value of T in table B11 and table the saturated liquid and saturated vapor region. And P2 similarly the saturated solid and saturated vapor region is listed according to the temperature in table B1. We have the saturated region in the point temperature, for example, in this area. In the table B11, the first column is temperature as shown. Gives the compressive saturated pressure in kilopascal. This is the for saturated water. Saturated water for values pressure and temperature. At the saturated water point we have the equilibrium between water and vapor. The next three columns gives the specific volume in the cubic meter per kilograms. Cubic meter per kilograms from the saturated liquid, evaporation, and the saturated vapor. In each mixture, because of the equilibrium between water and vapor, we may encounter with three types of state in the control volume. The first of those columns gives the specific volume of saturated liquid. The third column gives the specific value of that saturated vapor, Vg, and the second column given the difference between the two saturated liquid and saturated vapor as defined in the previous section. Table B12 listed the same information as table B11, but the data are listed according to the pressure as mentioned earlier. In the table B12, the next picture in the next page, table B12 listed the same information, but we have saturated pressure at our norm, for example, as would be read the temperature and other properties of the, for example, steam in this table. An example, let us calculate the specific volume of saturated steam at, for example, we should read this at T saturate equal to 200 degrees centigrade, having a quality of, we have two independent properties to describe the substance state. They are independent of temperature and quality, or pressure and quality. Vapor is 7/10. So from the previous table, for the 20 degree, we don't have the information, but we can read from the table. From the table we can obtain the Vf equals to and Vg equals to so we can obtain V equals y minus x plus x Vg. Plus multiply to, now we can calculate V, the specific value of the stated as the water steam. Table B13 as same as this table B12, B13 gives the properties of superheated, properties of superheated vapor in the superheated region. Pressure and temperature are independent properties. So we have a note here in the pressure and temperature. Excuse me, in the superheated region, pressure and temperature are independent properties. Therefore, for each pressure, a large number of temperature are given, and for each temperature, 4 thermodynamic properties are listed. The first one being specific values, the second, so we have a different tables in B13. The table B13 shows the, for example, temperature and pressure are independent. Independent properties, so can interpret the state. For example, for a specific pressure we have a large amount of temperature and a specific and the specification for the superheated water, and for example the pressure 50 kilopascal, we have different temperature. The same condition also is for the temperature as the base property. In this case also we have temperature and pressure as independent properties. We have in the superheated region, pressure and temperature are independent properties. Therefore, for each pressure, a large number of temperature are given in the previous picture, and for each temperature, 4 thermodynamic properties were described in this table. Table B14 in this case gives the properties of the composite liquid, compressed liquid. To demonstrate the use of this table, consider a piston and a cylinder that contains 1 kilogram of saturated liquid water at 100 degree temperature, for example in this point. These properties are given in the B11, and we note that the pressure is 1 from B11 for T equals to 100. The pressure is megapascal and the specific volume is suppose the pressure is increased to 10 megapascal. So if pressure increase to 10 megapascal, while the temperature is held constant at 100 degrees centigrade by the necessary transfer of heat Q. Since water is likely compressible, we would expect a slight decrease in the specific volume during this process. Table B14 as here gives a specific volume of, for the 10 megapascal we have no from P14 this is only a slight decrease, and only a small error would be made if assumed that the volume of compressed liquid is equal to the specific volume of saturated liquid at the same temperature. In many situations, this is the most convenient procedure, particularly when compressed liquid data are not available. It is very important to note, however, that the specific volume of saturated liquid at the given pressure, for example 10 megapascal, not given a good approximation. This value from table B12 and the temperature is more greater than these two quantities and is which is error by about 40%. Table B15 of the steam table gives the properties of saturated solid and unsaturated vapor that are in equilibrium, as also solid and saturated vapor. In equilibrium, and also water, solid and liquid in equilibrium. The first column gives the temperature and the second column gives the corresponding saturated pressure. As would be expected, all these pressures are less than the triple point pressure. The next two columns give the specific volume of the saturated solid and saturated vapor. Appendix B also includes thermodynamics tables for several other substance refrigerant fluids such as R134A and R410A, ammonia, and carbon dioxide. And the cryogenic fluids, nitrogen, and metal. In each case, only two tables are given: saturated liquid vapor listed by temperature and superheated vapor also in the table 1.3. Let us now consider a number of examples to illustrate the use of thermodynamics tables for watt and for the other substance in the appendix B. The next section, there are various problems related to this section and previous section. The next section in this chapter is thermodynamics, dynamic surface.